Hello there. Hello there. Hello there. Hi, I'm Brenden. Today I want to talk about Bitcoin hardware wallets and kind of like this guy. This is a Trezor. Also have a Ledger here. Ledger Nano. You may have seen one of these. So I want to talk about these, and specifically what I want to talk about is recovery seed storage and backup. I wrote a Python CLI tool for seed storage using a one-time pad for encryption. If you are a Bitcoin / cryptography nerd, kind of like me, then maybe this stuff is interesting to you. If so, then I hope you find this entertaining. All right, let's get on with it. So, seed OTP. What's the problem we're trying to solve? First of all, well, if you have one of these, like a Trezor or whatever, then you probably have some seed words, recovery seed words that you need to store. You may have something like this. This is a product called CryptoSteel, and it is a seed storage thing made of steel with little slots for steel pressed characters where you can write out the words, and you can use this to store your seed phrase long term. You can put that in a safe or a safe deposit box or under your mattress or whatever. However, storing your seed words is it's not straightforward. It's a little complicated. So I'm not going to go into a ton of detail on seed words or how they're derived or whatever, but you can check out BIP 0039. That's the Bitcoin Improvement Proposal, I think is what it stands for. And there's a lot of detail there on the seed words and the dictionary, and which words are used and how those are encoded and so on and so forth. Okay, so just generally speaking, let's talk about these seed words. If you have one of these and you have some words and you want to store this in a secure fashion, you need to make sure that nobody else gets their hands on that, obviously. So you can put that in a safe and bury it in your backyard, or you can put them in a bank vault or something. However, if for some reason someone comes upon those words, they can get one of these, pop those words into it, or just use a software wallet like Electrum or something, and then they can take all your Bitcoins if that's what they want to do. So that's not good. What can we do about it? Well, that's what I'm talking about. Before I go there, though, hardware wallets also have their own issues, and there's a website called wallet.fail where some researchers have gathered some data and done some research on which wallets are easy to break and which are not. The Trezor, for example, has some vulnerabilities, as does the Ledger. However, generally speaking, as long as you don't lose these and you protect them with a passphrase, then you're going to be pretty okay. However, if you do lose one of these, you're going to probably want to recover from your seed and move your funds quickly, because as soon as someone extracts the private key from inside of this device here, which is possible, no matter how hard the hardware vendors try. As soon as that happens, they can take all your coins, right? So that sucks. All right, we have a dog here, the chicken, and a gerbil. So what can we do? There are two kind of main ideas, I think. One is this Horcrux idea, as I call it, or like other people call it. I didn't come up with that. There's two ways to do this. One is that you actually break the seed itself into multiple pieces. So, for example, if you have 12 words, then you would take the first 3 and the second 3 and third 3 and fourth 3, whatever, and store those in separate places, separate secure places. That's one way to do it. A much better way, arguably, is to use a multisig wallet So you can use like a 2 of 3 or a 3 of 5 multisig wallet and store those individual wallets and seeds separately in separate places. Now, this is maybe slightly impractical depending on who you are in your life and everything. So, consider that. But alternatively, you can use a one-time pad to back up your seed, right? So a one-time pad is just a simple way of encrypting stuff. And the nice thing about this is that it's pretty simple, it's straightforward. You can still use multisig with a one-time pad. So for example, you can have a 2 of 2 multisig wallet. So you would buy, say, one ledger, buy yourself a ledger, and then you'd also buy yourself a Trezor, and you would use Electrum or something to make a 2 of 2 multisig wallet. And in order to make any transaction, you'd have to have both of these guys and sign the transaction with both of these. So you could store this in your pocket, and you could store this perhaps, I don't know, under your mattress or whatever, and it would be very hard for someone to steal your funds. Realistically, if you want to store things safely, probably the best thing to do, aside from doing all these other things, if you want to be really crazy, is to have multiple wallets and just kind of store little pieces of everything all over, and try not to lose it. So if any one single wallet gets hacked, then at least you won't be broke, right? Okay, moving on. What's a one-time pad? A one-time pad is a very simple encryption method. It can be applied without using a computer. It's pretty easy. You can just do it like basic math, pen and paper if you want. It's considered to have what's called perfect secrecy, which means that there's nothing about the key or the ciphertext that really reveals any information about the image. In fact, to the untrained observer, or to any observer really, if you have nothing but basically a set of words or letters or whatever that have been encoded with a one-time pad, then it's indistinguishable from random, effectively, assuming that your random number generator is decent. Of course, you can still use this with multisig if you want. All right, so one-time pads are pretty cool if you haven't heard of this before. A little historical context, and I just copied these from Wikipedia, which is a great source for all kinds of information, but let's just talk about some of the historical uses of a one-time pad. So one interesting use is that during World War II, they used this voice scrambler, and what they did is they injected noise into the signal that was encoded with a one-time pad, and then they basically removed the noise on the other end with the same one-time pad, and so they could broadcast signals, and nobody else could listen to them because it would just sound like noise to to whoever doesn't have the key. Yeah, so the hotline between Moscow and Washington, D.C., which was established after the Cuban Missile Crisis, originally used a commercial one-time pad system, which was interesting. I didn't know that until I read this this bullet here from Wikipedia. What else? U.S. Army Special Forces used one-time pads in Vietnam, and during the 1983 invasion of Grenada, U.S. forces found a supply of pairs of one-time pad books in a Cuban warehouse. Interesting. These are a couple historical one-time pads. There's one from the NSA there. I'm not actually totally sure how to use that one. That's an interesting one. And then there's some miniature ones from East German former intelligence agencies. Cool. I got that one. The one on the left is from Wikipedia. The other is from a website about one-time pads, which I'll include a link to as well if you want to check out. What else? Another way that they're used is through number stations, which you can hear in the background. And number stations are basically these radio stations that just broadcast some recording of someone, usually a person, I mean maybe a robotic voice or whatever, just repeating numbers and over again, seemingly randomly. Sometimes there's a little jingle or something, which is kind of cool. They sound pretty creepy though, if you listen. So what's interesting is that there are probably, I think there are multiple websites that track these number stations. There are probably number stations active right now. Although frankly, anyone can create a radio transmitter and just like blast recordings of someone reading numbers into the atmosphere. Anyone can do that. So who knows if they're legit or not? There's really no way to know. But anyway, as recently as 2009, a gentleman, Walter Kendall Myers, was charged with conspiracy to spy for Cuba, and he was caught receiving and decoding messages from the Cuban Intelligence Directorate using a one-time pad. Fascinating. One-time pad. How does it work? A very simple encryption. It's kind of like, you can think of it as a lookup table where you have, your message is combined with a key, and the key essentially is like it can maps to something, some entry in your pad essentially, and your keys are just randomly generated. The receiver of the message just does the reverse operation, and that's how you decode it using the exact same pad. Generally, both the sender and the receiver need to know which pad you're using, and you would communicate that ahead of time. So you might, for example, have a book full of pads, and then there's a page for every day of the year or something. And depending on what day it is and when you read the message, you would use a different pad and a different set of keys, right? Pretty cool. So as an example, suppose Alice wants to send a message hello to Bob, and Alice and Bob have securely shared a pad. This example, by the way, is copied directly from Wikipedia, so if you want to follow along, you can just look at it. But anyway, you have a really simple pad. Depending on the position of the word, your key characters is changed, and you basically just select the key from these options, right? Okay, so to encrypt hello using the pad, the following function is implied. So to generate the ciphertext for each word, you take the message for each word, like 1, 2, 3, 4, 5, add the key, and then mod that with 26. There's only 26 possible characters, so if you go over, you basically are wrapping it around. To decode, you basically do the reverse of that. Pretty straightforward. You take the ciphertext, subtract the key, again, mod 26. So to illustrate, to encrypt, right, I have hello, my message, HELLO. Each character corresponds to, in this case, it's illustrated as an integer, but you could treat it as bits or whatever. And I'm taking that value, and then I'm going to add the key, so it's going to be basically m plus k, and then mod it. So h turns into 4 because 7 plus 23 for h and x is 30, and when you mod that, you're left with 4. And so on and so forth. So you can go through each one of these, and then our new ciphertext is going to be EQNVZ, right? Pretty straightforward. So to decrypt it, we'll just do the reverse, right? Take our ciphertext, which is EQNVZ. Yep, we have a key. Our key is going to be XMCKL, which is the same key used to encrypt, if you look before, right? Okay, so now we're going to take the ciphertext minus the key, and then again mod it, and then repeat that and so on, and you end up with 7, 4, 11, 11, 14, HELLO, right? Back to the original message. Pretty simple. Cool. All right. So what are the gotchas with applying this to the seed words? Well, there are a few problems. One, notably, is that when you encrypt the seed words with a one-time pad like this, your resulting set of seed words is not actually BIP39 compliant. And what I mean by that is that the BIP39 specifies a checksum at the end, which is based on the first, I forget how many bytes of this set of bits, basically. Sorry, bits, whatever. Because we're simply changing the words, it completely breaks the checksum at the end. In other words, if you were to take the encrypted words that you generate using this Python tool that I'm going to show you in a couple of moments here, if you take the words generated from that and you tried to initialize or recover a wallet with them, it would just fail because it's invalid. The problem with that is if someone were to get those seed words and they realize that the seed was invalid, then they may be able to infer that you've applied encryption to your seed words. And that in and of itself kind of reveals some information about the seed. In fact, it might let the person who's trying to, the attacker, let's say, it might tell them that they've encrypted that. It may even hint as to what method was used. However, it doesn't tell you anything about the key or anything like that. So realistically, I don't think it's a problem, but something to consider. Perhaps in like a version 2 of this, I could redo it in such a way that the checksum is regenerated. It's possible to do it, and the downside of doing it that way is then it becomes extremely impractical to apply the one-time pad by hand, which is a thing that I really wanted to be possible because it means that you can do this without a computer, which has some important OPSEC implications. Okay, if you lose all the seed words or the one-time pad key, then you're in trouble. Password managers are also not necessarily 100% reliable, since I recommend in the documentation, like in the README, that you put the OTP key, the one-time pad key, into a password manager, and that has its own issues. You could store it a different way. I would leave that up to you. You also need to be able to generate truly random numbers. That has to be a thing. And one more note, I refer in the documentation to this as a sort of multi-factor auth. And the reason I call it that is because if you imagine the one-time pad key as just a random string that you don't know, you have a copy of it because it's stored in a password manager, but you don't actually know the string. You do, however, know the seed words. Let's pretend you know the seed words because you have them written out on a piece of paper, the encrypted seed words, let's say. What that means is that you can't be coerced into giving up the OTP key or anything like that. The only way to get the OTP key, I guess, would be to extract it from the password manager. But I guess if you know the password to your password manager, then that kind of breaks down. However, as with pretty much everything in security, security is mostly about adding layers of deterrence rather than any idea. Like the idea of like absolute security or anything is kind of practically infeasible for the most part. So, okay. I'll include some links to some of the stuff I talked about, and let's jump through to do a little code walkthrough and do a demo. Okay, how does that sound? Sound good? Cool. If you want to check out the code, head on over to GitHub. You can go to my GitHub profile /seed-OTP and check out the code. There it is. It is a simple Python project. Let me reload. It's messed up. There we go. There's a little SVG animation that shows what it's like. I'm going to show you in a little more detail how to use it. I'm going to demo it first, and then I'm going to do a little code walkthrough. Assume you've got a fresh Python environment here. I'm just going to make a brand new virtual env. Make dir temp, and then I'm going to cd into temp. I'm going to say virtual env venv, boom. Okay, source my virtual env. Having a hard time speaking and typing at the same time. Activate. All right, I have virtual env here, so I'm going to install seed OTP. Boom. That's going to fetch it off of PyPy, or that's going to fetch it off of, yeah, PyPy. PyPy is the right thing, right? Yeah. All right, got it installed, so now I can type seed OTP --help, prints out some help. There are 4 commands that you can run. The first one that I'm going to show you is to generate the seed. So let me show you what happens when you run generate. So let's just walk through the code. If I go into main and I look for generate right here. So this code uses the Python click library, which is a really nice library actually if you are writing any kind of Python CLI tool. It's pretty good, provides a bunch of stuff out of the box. Check it out if you're interested in it. So, all right, so what does it do? Pretty simple. You run this, it calls this generate key function, which is in here. And what it does is very straightforward. It's just going to, for the number of words that there are, it just generates a random number between 0 and 2048, right? 2048 is equal to 2 to the 11. Is that right? 2 to the 11? Yeah, 2 to the 11. Okay. Because there are 11 bits used, or basically every word corresponds to 11 bits of data. Okay, so in this it's calling secrets.ranbelow, and this is a bit of a rabbit hole, but I think it's important, worth talking to talk about how we're actually generating these random numbers. So this is going through the Python secrets library, which is new in, I think, 3.6. Yeah, new in Python 3.6. And there is this ranbelow function. So what it does is it's actually just calling the system, there's a system random method in Python. Where is it? Python system random. And underneath the hood, it is calling to, well, it depends on your OS, but like on Linux, it would be dev urandom, which is the kernel random entropy source. If you try to implement a one-time pad and your numbers are not, your random numbers are not actually random, then you've got a problem. So, all right, moving on. What happens? All right, so we basically generate a bunch of random numbers, and that's that. So if I run this in my terminal, I say seed OTP generate. What does it do? Whoops, I have to tell it the number of words I want. So I'm going to say I want, and usually 12 or 24, depending on which thing, or which like model and vendor you're using. Okay, so I do seed OTP generate 12, and it prints out this OTP key here. So this key, this is the key base 64 encoded. You can actually see right here how it's encoded. It is encoded just using the Python pack. Basically, the bytes are just kind of smashed together, and then there's a 4-byte checksum at the end, which is just a the first 4 bytes of the SHA-256 digest of that key. That's so that you can validate the key in case someone is like typing it in by hand. Maybe you wrote it down on paper. Provide some validation there. So, all right. So what's interesting is that you can now take that key if you want, and you can pass it back into seed OTP. You can call this check key command here, and you pass the key like that. And what it's going to do is actually decode the key, the OTP key there, and then print out the individual keys for each for each word, basically, right? So these numbers correspond to the position of the word in the dictionary that each of these gets mapped to using this one-time pad, right? So what can you use this for? Well, if you wanted to apply the one-time pad by hand, you can use this as a shortcut, or you can do it yourself. You also don't have to use this code. You know, you can just use it as a reference implementation, or you know, just for fun, whatever you want. Generally, I would probably want to encrypt. So let's see, seed OTP encrypt -- help. Let's just see what it says. There are a few options here when it comes to the actual encryption and decryption. The input is the OTP key, so we have one right here. Let's take that. And then your list of words. So I'm going to need 12 actual words. They have to be words that are actually in the dictionary, otherwise it does not work. I'm just going to copy the words from my example over here on GitHub. Whoops, accidentally changed the tab. Okay, I'm just going to paste those in there, and when I run this, it's going to spit out a new set of words. Okay, so if I were using this tool to back up my seed words, I would now write down these words. Now keep in mind the order matters. The order is very important, so don't mess up the order. Of course, if you were going to do something like this, you would double check that you can actually go through the reverse process and do the recovery before you consider it done, right? You probably wouldn't even want to use the wallet until you have successfully gone through the whole recovery phrase with it. Okay, cool. So now that we have that, let's go ahead and try the decrypt. So decrypt is basically exactly the same as encrypt, but the reverse, as you'd expect. Just to show you the options again, it's pretty much the same. Pass it the key, and then pass it the list of words. What is different this time is that the list of words we're going to pass in are going to be the words that came out of the encrypt process. So we copy these, paste them in, involve, unit, remember, badge, hollow, prefer, menu, they, table, end. That took a while, and boom, there we are. So those words should match our input words, which I think they do. Abandonability, able, yeah, that looks right. Cool, that's it. So that's a one-time pad. That's pretty much all it does. There are a few other options here I didn't mention. One specifically is that there are actually multiple different language word lists. So if you wanted to get even crazier, you could try maybe using a word list in a different language or something. That would be pretty interesting. Keep in mind that you would need to use your wallet in that language as well, or you could like manually map the words if you want. It would probably be very confusing to anyone who saw, 12 Japanese or Italian words written on a piece of archival paper somewhere, what that means. Realistically, I think nobody would have any idea. You could also like provide some more, you could like have like a random set of words as a decoy next to them or something. I don't know. Or you could put a bunch of like lorem ipsum stuff all over the place, and people would just think it's gibberish. They'd have no idea. I would hope that you would be able to find that code again. So, okay, so let's just walk through what I just did there as well. Let's look here in main.py. So I ran check. I'm not going to go through what that does. It's pretty straightforward, but let's just take a quick look at encrypt first. So encrypt is going to, first of all, decode the key, right? So that OTP key gets decoded and it gets split out into two parts. The first part is the number of keys. The second part is the actual list of keys. Then the next thing, it's going to load the word list. That comes from the dictionary that is bundled. I'll just show you quickly how or where that is. It's in here, word list. You can see all the dictionaries. There's English, or word lists, French, so on, right? Okay, so it loads the words, and then it does this encrypt. So encrypt takes in the number of keys, the key list, the word list, the words to the index. So basically every word gets mapped to an integer, which is just the index position of that word in the word list and the words. So let's look at the encrypt function. It is pretty straightforward. It should look a lot like what I showed you earlier in the slide. And basically for each word, it pulls out the word itself, MI, which is the word, the message index, then the actual key, and then we get the ciphertext index out, which is just going to be the index of the message plus the index of the key, and then modded by the length of the word list. In the example that I showed you before, we were using a word list of length 26 because we were just using alphabet from A to Z. So in this case, our word list is 2048 in length as defined by BIP 39. And that's it. So for decrypt, it's literally the same. This code looks almost transposed. The only difference is essentially the inputs to this. This is going to be the ciphertext index, the key, and then the message index, which is computed by the ciphertext index minus the key modded by the length of the word list. And then the message is just, you look up the message index in the word list and output the word, and that's it. Pretty straightforward. All right. Well, that is it. I hope you got some enjoyment out of that. I hope you enjoy listening to number stations. They are fascinating. There's a lot of them out on the internet, and they're all pretty creepy. So thanks for watching. Take care. Bye-bye.
4, 6, 5, 4, 3, 4, 6, 5, 4, 3, 2, 5, 7, 2, 5, 7, 1, 4, 3, 1, 4, 3, 0, 0, 0, 0, 0,